All right, we're on chapter 3 on determining change derivatives, and this is section 3.7 on limits of quotients and L'Hopital's rule. So we're just going to kind of review limits really quick, and then we'll get into L'Hopital's rule. So, limits are used to define the continuity of a function modeling data sets, and limits are also used to examine the behavior of a function at a point, as well as its end behavior. So the replacement rules, which we basically call direct substitution, are used as a first effort to evaluate the limit at a point. So if we have some f of x over here, and we want to find the limit as x goes to c, we just plug in c and we find out what f of c is. And if f is a function in the form ln of x and c is greater than 0, so the key here with ln's has to be greater than 0, then when we do it, it's going to be that way. So there's the limiting factor on ln that we have to worry about. Now, with the end behavior analysis, basically we look at how the end behavior is for whatever function we're looking at. So as x goes to plus or minus infinity, as x goes to 0 from the right for ln of x, because if you think about it, ln of x is going to go something like that. And so, it's going down to 0 for the ln of x. It can never get to 0, but it's going to get closer and closer and closer. And when the end behavior of one or more of the functions is unbounded, further evaluation may be necessary. So if we ever run into that, you'll see what we're talking about there. Now we have our regular limit rules we've been using. We have the constant rule. The limit of a constant is just that constant. The constant multiplier, we can pull that constant out in front, and then we just take the limit of the function left over. If we have two added together, we can break them apart into the limits of the two different functions. If you have a limit of two of them multiplied together, we can break it apart into the limit of both of them multiplied together. Same with dividing. And then we can also cancel. So if we can break it apart and then cancel, we can do that. And then that's going to be the limit of one over the other one. Okay. Now, each of these limit rules can be written for end behavior limits as well. So as x goes to plus or minus infinity instead of just x going to c. Now, in cases where the limiting behavior of one or more of the functions is unbounded, we are going to have to, again, do further analysis if necessary, if we ever run into that. But this is where we're really getting to using L'Hopital's rule. So we're going to get an indeterminate form of quotients and products. So what we're going to do is when we plug in something, replacement's generally used as our first step, as we talked about. But what might happen is we might get something like 0 over 0, infinity over infinity, or 0 times infinity, which all of those are known as indeterminate forms because without further analysis, we don't know what the actual limit is. What's 0 divided by 0? I don't know. What's infinity divided by infinity? I don't know. What about 0 times infinity? I don't know. And so what we're going to have to do is we're going to have to go to the next step, which is using L'Hopital's rule. We're actually going to take a derivative. So if we end up with 0 over 0 or infinity over infinity, what we're going to do is we're going to take the derivative of the numerator, the derivative of the denominator, and find the limits there as x goes to c. Okay. Now that's, provided that the limit on the right side of the equation does exist. So that's going to be kind of a key. Now the ratio of the two functions, whether f of x over g of x or the ratio of the slope functions, both of those are going to have the same limiting value. And that's why we can do this. We can take and find the derivative and then we can get it. Now, one thing might happen is we might get to this stage and it's still going to be 0 over 0 or something that doesn't make sense. And then that's when we have to do this multiple applications of L'Hopital's rule. And so then we're going to take the derivative of that and then find that one. And so we're going to have to do sometimes multiple steps where we take extra derivatives. What if we end up with something like 0 times infinity? This one was 0 divided by 0 or infinity divided by 0. But if we have something like that, what we're going to have to do is we're going to have to basically manipulate the original problem and then after that apply L'Hopital's rule. So what we're going to have to do is we're going to have to, if it's say f of x times g of x initially, then what we're going to have to do is take one of them to the denominator, change the from a positive to a negative exponent, and then see if we can evaluate it at that point. So that's going to be the key thing, is kind of manipulating the numerators and denominators to make it so we don't have 0 times infinity. We have, something, if we get it to 0 over 0 or infinity over infinity, that's fine, because then we just apply L'Hopital's rule directly and we're done there, and we can find it. So that's going to be our steps for solving these kind of limits. And so what we'll do is we'll pause here and we'll come back and actually start solving limit problems.